This is the second video in a series of videos where I'm looking at the solution to the MOKASA joint examination, March-April session, 2019, Physics Paper 1. I've already looked at question 1 all the way to question 5, and in this video I want us to look at the solution to question 6. In question 6, we are told that the figure 3 shows a rubber bladder filled with air and fixed at the bottom of a water container and held with a cotton thread or cotton string. So the diagram is given here. So this is the bladder filled with air. It's more like a balloon. There is a string here which ties it to the bottom of the container, and I believe that if this string is cut, then the bladder is going to move upwards. We are asked to state and explain the observation made when water is heated gently for a few minutes. So let's see what happens. So I'd want us to start looking at some of the forces which are acting on this object, which is the bladder, which is immersed in water. One of the forces which is acting on it is its own weight, downwards, like that. This is the weight of the fabric of the balloon plus the weight of the air inside. That total weight will be represented by W. So that force is acting on this object as a whole, vertically downwards. The other force which is acting on it is the up thrust. Up thrust. We know that if an object is immersed in a fluid, in this case the fluid is a liquid and it is water, then that object will experience an upward force due to the fluid. And that upward force is referred to as up thrust. Like we said, if we cut this string, this balloon or bladder will rise. That means there is a force in this string, which is tension in the string, and it tends to pull the bladder downwards. As it is in this particular situation, it is in equilibrium. That means the sum of upward forces is equal to the sum of downward forces, which is T plus W. Now another concept which we will remember is this, that upthrust is given by the density of the fluid, the volume of the fluid displaced, times the gravitational field strength. This is an equation which is used to calculate the upward force acting on this object due to this fluid. Now what is density? Density is mass over volume. If we heat up this water, actually it is warmed slightly. State and explain the observation made when the water is heated gently for a few minutes. When we heat this water, it's going to expand. So it will expand. So the volume increases and the density will therefore reduce. When the density reduces, this density is going to reduce. By the way, this V and this V, they are different. Here I'm talking about the volume of any amount of water. This is the volume of the water which is being heated. When you heat that water, it's going to expand, but its mass remains the same, so the density of the water itself is going to reduce. How about this V? This V is the volume of the water displaced when this object is immersed in the water. So distinguish between this V and this V. They are not the same. This is the volume of the water displaced, which actually is equal to the volume of this object, which is the bladder. Because if any object is immersed in a liquid, then the volume of the liquid displaced will be equal to the volume of that object. So this V is the volume of the water displaced which by extension is equal to the volume of this bladder, because the bladder itself is completely immersed. Remember, if it is partially immersed, then the two are not the same. We are going to assume that the bladder does not expand. No expansion takes place here. The expansion is in the water. If that happens, then this V remains the same, but the density of the liquid has reduced. If that happens, then the upthrust will reduce, because these two are constants. They do not change. So the upthrust has reduced. If the upthrust reduces, the weight of the bladder and the air, remember W is equal to the weight of the fabric plus the weight of the air inside. This does not change. But if this reduces, then it means that the tension is going to reduce in order to maintain this equilibrium. So if we subtract a certain number from here, we must subtract a certain number from the right in order to maintain this equilibrium here. So the tension in the string will reduce. So that is it. The water expands, its density decreases, upthrust decreases, and in order to maintain equilibrium, the tension in the string reduces. And remember, we are making this conclusion because we are assuming that when the water is heated, it does not expand the air inside here, and therefore the volume of the bladder remains the same. But if the bladder were to expand, then we would expect some different results here, depending on which one expands more and which one expands less. So in order to make this question clear, I guess we would have been advised to assume that the bladder does not expand. So let's look at question 7. So in question 7, we are told that the figure 4 below shows a pipe of varying cross-section, 3 vertical tubes X, Y, and Z of the same diameter are fixed to the sections A, B, and C of the pipe, respectively, as shown in the figure. So there are these vertical pipes, which actually are manometers. And of course, there is this tube. You can see that this one has got a slightly larger cross-section compared to this, and A has got the largest cross-section. So given that the water flows in the direction shown by the arrow, indicate on the diagram the relative levels of water in X, Y, and Z. Now in this question, we have to remember that when a fluid, in this case it is water, flows through a pipe of varying cross-section, it moves faster where the cross-section is smaller, because the fluid is incompressible. This water here is incompressible. So it's going to move faster where the cross-section area is smaller. And when it moves faster, the pressure is going to reduce. So the pressure that we have here in the water is much, much smaller than the pressure we have here. Now, in A, it's going to move with a slower speed than in C, because the cross-section area is larger in A than in C. So I would rather we compare the pressure in C and the pressure in A. There will be more pressure here and less pressure here. So the height of the manometer in Z is smaller than the height of the manometer in X. So comparing these two heights, this is what we are going to have. Now I'm going to have a height which is smaller here than in X. So when you compare this height with what I want to draw here, it must be smaller. So I'm going to maybe assume that the level of the water in the manometer here will be up to that much. So look at this height, compare it with this height. You can see that the height here is smaller, showing that over here we've got less pressure in the liquid compared to the pressure here. So the pressure in the liquid is highest at this point, X. And here it's a little bit low because the speed here is higher than the speed over there. Now when we come to this level here, we've got much higher speed than in C. So the pressure at this particular point here will be lower than the pressure at this point. So here we are going to have a much smaller height, showing that the pressure has been reduced significantly. So remember, this is the way it's supposed to be, because the highest speed is experienced here. So we can have a very big arrow showing that this is where we have the highest speed, followed by the speed here. You can see that arrow is much smaller than here, and here it is the lowest speed. So that is the way it is supposed to be. So the point that we want to make over here is that when a liquid flows through a pipe of varying cross-section, it has highest speed where the cross-section is very small compared to where the cross-section is very large. So higher speed, low speed. The next point is this: when the speed increases, the pressure in the liquid is going to decrease. And these vertical tubes, they work like manometers. A manometer is a piece of apparatus that is used to measure pressure in a liquid. For example, in this case, it can be used to measure pressure at this particular point. So when the speed is very high, the pressure is very low, and therefore the height will be small. Remember, pressure in a liquid is given by the density of the liquid times the height times the gravitational field strength. We are talking about this height here. That is the height that we are talking about. So when the pressure is highest, of course the height will be highest. So let's move over to question 8. Now in this question we are given that a smooth wooden plane is inclined at an angle of 30 degrees to the horizontal as shown in figure 5 below. An object of mass 10 kilograms is pulled steadily up the plane by a force of 60 newtons. Determine the velocity ratio of the inclined plane. So we will remember that velocity ratio of a machine is usually given by distance moved by the effort divided by the distance moved by the load. This is the load. Of course, it should be drawn in such a way that it is in contact with the inclined plane. So we have to assume that. So the load is actually the weight of this block. It acts vertically downwards. Weight is given by mg. The mass is 10 kilograms. G is 10 newton per kilogram. So the weight is 100 newtons. So the effort is this arrow here. So this E is the effort, while this is the load. The load actually moves through a certain vertical distance here. h. From here to here is h. So this is the distance which is moved by the load. The effort moves through a distance along the incline, like that. Notice that since the effort is in this direction, the distance moved by the effort is also in the same direction. That distance is parallel to the arrow here. Notice the load. The load is also moving in a direction which is in the same line of action as the load. Although the weight of the object acts vertically downwards, the object appears to be moving vertically upwards, and this is because there is a component of this force which actually tends to pull the load upwards. So let's see whether we've been given any of the distances by a force of 16 newtons. The object, an object of mass 10 kg, is pulled steadily up the plane by a force of 60 newtons. Have we given any of the distances? I don't think so. None of the distances is given. Now let's look at how we can make, suppose let's call this distance here L, length, and this is h. Let's look at the relationship between L and h. The distance moved by the effort is actually L. The distance moved by the load is actually h. And this appears to be, this is the hypotenuse of this right-angled triangle divided by the opposite. When we divide the hypotenuse by the opposite, we remember this acronym, SOHCAHTOA. The sine of an angle is equal to the opposite over the hypotenuse. The cosine of an angle is equal to adjacent divided by the hypotenuse. The tangent of an angle is equal to the opposite over the adjacent. But here I have hypotenuse over the opposite. Hypotenuse over the opposite. It is not opposite over the hypotenuse. So if I can be able to say that this one is equal to 1 over sine of the angle theta, I would be correct, because sine theta is equal to opposite over the hypotenuse. But we are given hypotenuse over the opposite. Another way of looking at this is like I can put a 1 there and then I make opposite over hypotenuse. Opposite over the hypotenuse. And we can see that opposite of the hypotenuse is the sine of this angle. So velocity ratio here is going to be equal to 1 over sine of 30 degrees. Sine of 30 degrees is 0.5. So 1 over 0.5 actually gives us 2. And that is the velocity ratio of the inclined plane. Efficiency. Efficiency of any machine is equal to, for this case, we are going to divide the mechanical advantage over velocity ratio times 100. Mechanical advantage of any machine is given by the load over the effort. The load is 100 newtons. The effort is 60 newtons. And we have 5 over 3. This will be the mechanical advantage. So for us to be able to calculate velocity ratio, we just need to divide mechanical advantage, which is 5 over 3. All this we divide by velocity ratio, which is 2, and we multiply by 100. So let's write it properly. So this one will be 5 divided by 2 times 3, and then I multiply by 100, and this will give us, so this is like 500 divided by 6, and that will give us 83.3. 83.3%. 83.3%, and that will be the efficiency of that system. Let's look at question 9. In question 9, we are given that the figure below shows a spiral spring when not compressed and when compressed by a mass of 4 kilograms. Determine the elastic potential energy stored by the compressed spring in B. Elastic potential energy. So over here, its original length, or the length when there is no load on it, is 8 centimeters. This is the new length with the load on it. And you can see that there will be a compression here. The length of the spring has changed by this much. In order to get this compression, which we are going to call E, we get the, in this case, it will be the original length minus the new length. The original length was 8 centimeters. The new length is 6, and we get a compression of 2 centimeters, and this is 0.02 meters. Now, the work done on the spring in compressing it is equal to a half times the force applied times the value of the compression. So this work done is equal to the elastic potential energy which is stored in the spring. Remember, when work is done on an object, that object gains energy. In this case, the type of energy gained is elastic potential energy. It's very important to realize that. So the amount of force which is applied to this spring is equal to the weight of the 4 kilogram mass, and that will be 40 newtons. 4 times 10. Remember, again, to get the weight of an object, we just need to multiply the mass times the gravitational field strength. So 4 times 10, I get 40, and the extension is 0.02. This will be, over here I'm going to get 0.01, and this one will be like 40 divided by 100, and of course this gives me 0.4 joules. So here I want you to recall the equation which is used to calculate energy stored in a stretched spring or compressed spring is given by a half times the force times the extension or the compression, and this one is also given by a half K E squared, where K is the spring constant. But in this case, we do not need to go to calculate the spring constant because we already know the force and the compression. So let's move over to question 10. So here we have it. In question 10, we are told that the bicycle pump shown in figure 7 below is one of the applications of pressure in gases. So this is a bicycle pump. Explain how the leather washer functions during the backstroke and the forward stroke. So let's see. Of course, you can see that the diagram over here is very neat. The backstroke occurs when we pull the handle. That's the backstroke. and the forward stroke is when we push the handle into this barrel. So, and over here, of course, we can see we have air at atmospheric pressure, because you can see this part of the barrel is open and it allows air to move either in or out. But over here, because this one is fixed onto the valve which is connected to the tubing of the tire, it means that the air inside here can be compressed, or we can make it to expand. So as it is right now, everything is under atmospheric pressure. When we pull this handle backwards like that, the washer will move backwards, and that means it's going to increase the volume of this gas inside here. But then the valve has closed during backstroke. Since it has closed during backstroke, the only way in which air can get inside here is via this section here. So the washer is going to collapse, creating a space here so that the higher atmospheric pressure can force air into this region, because the pressure over here has become lower than atmospheric. Remember, we are starting with a situation where the pressure here is atmospheric and the pressure here is atmospheric. Pulling the handle backwards increases the volume of this space, and therefore the pressure is going to reduce. The higher atmospheric pressure will apply a bigger force on the sides of the washer, forcing it to collapse. When it collapses, it creates space between the barrel and the washer, and therefore air will move into this region here. So, explain how the leather washer functions during the backstroke. The leather washer is going to collapse, allowing air to move into this space here. How about during forward stroke? During forward stroke, the volume, remember we've got some air moving into this region here. We've got more air molecules now inside here than before we pulled the handle backwards. More air. Now we are tending to compress that air by reducing its volume. So pressure is going to increase here, and it will be higher than atmospheric pressure. But this air cannot escape back here, because the amount of force it is exerting on the washer is such that it tends to make the washer to press firmly against the walls of the barrel. So in this section, no air can escape now in this space here, back in this region. The only way that air can escape is via the valve. So it's going to force the valve to open, and air will move into the tube. So during forward stroke, the washer will remain firmly pressed against the walls of the barrel because of the way it is shaped, and that will force the air to escape via the valve. When it escapes via the valve, it actually moves into the tire, into the tube. And those are the answers you would give for 10A. So during backstroke, the washer is going to collapse, allowing air to move into this region because the valve has collapsed. It is shaped in such a way the higher atmospheric pressure tends to make it to be more curved, and when it is more curved, it leaves a space between its outer surface and the surface of the barrel, and therefore air enters into this region. During the forward stroke, it is shaped in such a way that the high pressure here tends it to make it to firmly press against the walls of the barrel, and therefore it cannot escape back into this region. It can only escape via the valve, and therefore it moves into the tube. Now let's look at question 11. Question 11 is how the greenhouse effect increases the average temperature of the Earth. So in this question, we are asked to explain how greenhouse effect increases the average temperature of the Earth. The first point to note is that the sun's radiation easily passes through the Earth's atmosphere. This is because this radiation, that is infrared radiation, has got shorter wavelength and higher frequency. Then it strikes the Earth's surface. The Earth's surface warms up and re-radiates that energy back to the atmosphere. But this energy or infrared radiation that it sends back to the atmosphere has got longer wavelength. Now, why is this? It's because the temperature of the Earth is much lower than the temperature of the sun. Therefore, the infrared radiation that it sends back to the atmosphere has got a longer wavelength. Now, this energy is easily absorbed by the water vapor in the atmosphere and the carbon dioxide in the same atmosphere, and of course other gases. And then the warm atmosphere in turn radiates back to the Earth. So it sends this energy back to the Earth, making it warmer than it would otherwise be. So it's just as simple as that.